Hi everybody, my name's Dane Comerford and welcome to this event as part of If Oxford Tonight on the challenge of remote engineering. So I'm now just going to let you get on with the event. I'm going to introduce some people from the UK Atomic Energy Authority who are exploring the challenges of remote engineering. So if you've not got your Menti website up, that's fine. It's going to be mentioned again. But I'm going to show, I'm going to stop sharing and pass on to John Whitty, who is a mechatronics engineer at RACE, which is part of the robotics division of the UK Atomic Energy Authority. So John, if you're ready to take over, I'll leave it to you.
Perfect, thank you. So thank you very much, and I'll just wait a moment while our slideshow takes over. So as mentioned, this is an interactive event. So throughout it, we'll be using Mentimeter to get your feedback and ask you questions and just generally find out what you're thinking. So as mentioned before, on your smartphone or another browser window, navigate to www.menti.com and put in our code, which is 2501783. I can see some of you already there filling in our initial question, just waiting for you. Just give you a couple of seconds just to have a quick look at that. And you can keep this tab open throughout the presentation for the other questions that we'll be asking later on as well. So just give you a few seconds to have a look at that. Okay, so if you missed it, don't worry, we'll come back to it and I'll read out how to get onto it every time we come up to another question. But today we are wanting to take you on a journey to some of the most dangerous places in the solar system. We won't leave you alone though. We'll be joined by exciting robots of all shapes and sizes that will help you on your journey. In general, we want to get you thinking about how robots can be used in these places to assist humanity in overcoming some of its biggest challenges. By the time we're done, we want you to understand how to use remote engineering to shape the future and save the world. But that's all very grandiose. So before we get too far afield, let's start thinking about some places that you might be more familiar with and see what we could learn if only we could go there ourselves and look. What kind of places can you think of? First test. Head over to Mentimeter, have a look at the question there, fill in any things you can think of that are particularly dangerous places to go to. And I'll give you a few seconds to have a think. While you're doing that, I'll have a quick look at a few examples that we've already thought of, starting with some places on Earth. So, for example, let's take the jungles and the tropical rainforests of the world. They're fascinating locations. They contain about 50% of the world's species. They also cool and regulate local microclimates, which causes the sort of limitation on the Earth's reflectivity, stabilizing ocean currents, wind and rainfall patterns, all sorts. Exploring these jungles, tracking their climates and the well-being and health of the flora and fauna within it is a huge task. And there's very little infrastructure within the jungle. And the jungle itself is a dangerous place for untrained personnel to spend too much time in. As you can imagine, this poses problems. Likewise, expeditions to the deep oceans are incredibly difficult. Some parts of the ocean floor are deeper than Mount Everest is tall. The deep sea is so unexplored, in fact, that we have better maps of the surface of Mars than we do of our ocean floors. Monitoring the deep sea might give us information about the ocean currents throughout the world and also help us discover new, never-before-seen species, not to mention we've got a lot of infrastructure that actually runs already along the seafloor, intercontinental internet fiber for one thing. So if any of you happen to be joining us from the US, then you have that to thank for it. Just like with the jungle, there are obvious hazards to working on and exploring our seafloor. Every 10 meters you descend underwater is the equivalent of another Earth atmosphere pushing down on you. At an average depth of over sort of 3,600 meters, this is 360 times more pressure than you experience on the surface. Breathing in that environment would be roughly as difficult as breathing with 140 Asian elephants stacked on top of each other standing on your chest. Not to mention, no significant amounts of sunlight penetrate past about 1,000 meters. So anything you're doing on the seafloor, you're doing in the dark. We don't actually need to limit ourselves to Earth, though. We can go further afield. We can look into the stars, where there are other fascinating locations that we could explore. The moon is overall not that far away in interstellar terms, but is a first obvious step if we're looking to inhabit other planets. It's the easiest nearby stellar object to get to, so any permanent inhabitation that we have might be tested there first. There are obvious challenges here too, obviously, with a lack of atmosphere, and despite it having been done before, landing people on the surface of the moon and getting them off again safely is no easy or cheap task. Similarly, perhaps you've been listening to the news lately, and if you have, I'm sure you've heard of this exciting possibility of life on Venus. And if we want to actually discover whether that's true or not, we'll have to explore the upper atmosphere there and look for more signs of what could be producing this phosphine gas that's being found. That atmosphere, however, is itself primarily made up of sulfuric acid, so that's not an easy feat either. Some of the most dangerous places that we want to be able to explore, however, aren't found in just completely naturally or in space, but are instead the result of human endeavor mixed with natural environments. Places where people have lived, for instance, that have been subjected to natural disasters can be incredibly dangerous to explore and repair. They can lock up access for vulnerable communities, and the people who are first responders to these disasters put themselves at risk regularly to assist those affected by them all over the world. As time goes by, we're likely to see the rate of extreme environmental events increasing due to the effect of climate change from global warming. Also dangerous right now are places like hospitals, where people who are susceptible to diseases regularly have to risk exposure to treat people suffering from them. So that's a few examples. So let's have a quick look at some of the places that you thought of and see what challenging environments you've come up with. Okay, woohoo! Look at that. So we're just going to have a quick look at a few of these. We had a look at deep sea already. Outer space, obviously, not just limited to a planet. You don't need to just say, oh, we're going to be on the surface of Mars or surface of the moon or exploring the atmosphere of Venus. There's plenty of interesting things you can do in deep space, and you've got to deal with vacuums and heat fluctuations and all sorts of things there. I see a lot of people mentioning nuclear power and nuclear fallout. Obviously, radiation environments are challenging environments, and we will be talking more about that later. So don't get too ahead of yourselves, but that's good. It's good. What else have we got there? Okay. Inside the human body, I really like that one. So there's sort of investigations in how to use robots within the human body itself, which has its own range of sort of nanobots. I'm sure you've heard of the general idea. It has its own range of challenges to deal with, and volcanoes as well. So again, on the natural disasters front, ideally you want to be able to monitor the volcano before it erupts, but actually spending much time near a caldera or burrowed into the earth to monitor these seismic events is very difficult to do safely. Okay, so good. You're clearly all in the right mindset, which is an excellent start. So sadly, as we are right now, you couldn't just walk into and explore these places. They're too dangerous for me or you to be able to survive without help. There is so much information that we could gain from going there. So clearly, surely, there must be something we can do, some sort of technique or tool that would allow us into these places without putting ourselves at risk. Now, the astute amongst you might be able to guess where I'm about to go from here. So joining me to help provide their expertise on how to use our knowledge of technology to help us explore these places are two experts from the United Kingdom Atomic Energy Authority, Craig Hickman and Helena Livesey. Helena is a mechanical engineer and also our expert on space robotics, while Craig is a software engineer with our cybernetics group, who works with radioactive robots for some cutting-edge science experiments. Craig is even joining us right now from one of our robotics test areas in Oxfordshire. Welcome to both of you.
Hello.
Hi.
Engineers like myself and my colleagues here use robots to help figure out how to get to places that humans normally can't. So potentially we could use them to explore these places to get the vital information we need out of them. Now, before we get too far into that, Craig, Helena, how about you tell us a little bit about how you use robotics in your day-to-day work? We'll start with Helena.
So I design and test tools that we use by robots to maintain future fusion reactors like ITER, which is currently under construction in the south of France.
Cool, great.
I write the software for robots that I use to move, cut up, and store radioactive components in the European Spallation Source, which is a neutron science experiment in Sweden.
Okay, so both of those sound super complex. So surely some of the places that we've discussed already must be easier than sort of future fusion reactors and spallation sources. Does that mean we can just bust out some robots and use them to explore? Helena, you're muted.
Sorry, unfortunately, it's not that simple. There are lots of different challenges involved for each environment, and they're very specific set to the particular area you're trying to access.
Okay, so let's try and find out a little bit more about some of these challenges then. Before we get too much into it, audience, another question for you here. Can we have the slide back up? Can you think of any potential challenges with using robotics to visit some of the places we mentioned before? So check out the Mentimeter link, put down your thoughts. Remember, as before, it's www.menti.com, and the slide will just be up in a moment. The code is 2501783. And if you have it open before already, then you can go back to that. There should be another question there. And hopefully we'll get the slide up and be able to show you the answers as we come in. So while you lot are navigating to menti.com, I'm just going to we're going to talk through with Craig and Helena a little bit about some other things about the challenges of using robotics. So Craig, I'm going to go to you first, I think. Primary challenges of using robotics, where do they lie as far as you're concerned?
Well, designing and operating these robots to be able to cope with these environments is certainly a challenge. Looking back to the jungle, which we showed earlier as an example, how could we get power to these robots? There are no plug sockets in the jungle, and the sensors, actuators, and computers make robots particularly power thirsty. Battery technology improvements lag behind our ever-increasing power demands, meaning a battery-powered robot may not be able to be operated for very long. So let's have a look at a robot that has been designed to be used in the jungle. If we go to the next slide.
I'm just really pulling it up.
No worries, so I'll let you get the slide up.
What is the presentation doing?
Sorry.
Let's quickly go to here, run show, share screen, screen 1, okay, share. So, there you go.
Yeah, so let's have a look at a robot that's been designed to be used in the jungle. So the solution the engineers who designed Slothbot here came up with was to use solar panels. This allowed it to be deployed for the months that are needed to survey the wildlife. And then we were talking about the challenges of remote engineering and what are some of the important factors. Well, perhaps most importantly, innovation is required. There's no instruction manual on how to design these systems, so we often have to find brand new ideas that have never been tried before. So again, looking at Slothbot here, you can see it has this unique method of moving around using wires between the trees. And innovation is often challenging, but it's also one of the reasons why working in this field is so exciting.
Cool. Okay, so Helena, what are your thoughts? Can you think of any particular challenging environments you'd like to highlight?
Yeah, so another challenging environment we mentioned earlier was space, specifically the moon. So sending humans to the moon is very challenging. So challenging, in fact, that no human has been there since 1972, and that's almost 50 years ago.
So why is it so difficult to get to the moon then?
Well, if you have to think about how you get there, you need years of training beforehand, a big expensive rocket that can get you all the way there and back again, and life support for the entire mission. But it's not just the cost. It's also very risky for the astronauts. There's lots that can go wrong that would put them in danger. By sending a robot, we can avoid spending all that money on training and expensive life support. And best of all, you can avoid sending a person into a hostile environment at all. So one way we could use robots for space exploration is to build a moon village. So we do still want to get humans into space, but we want to make that as safe as possible. So the idea here is that you would send a fleet of robots first, way before any humans get near the moon. These robots would carry out a few different tasks to make the environment safer for the astronauts. So if you move to the next slide, John, show an example. And this is a concept from the European Space Agency. It shows a robot using moon dust to 3D print a hard outer casing for a human habitat. This will protect astronauts from the radiation you get on the moon. The robots would also use resources on the moon to produce air for the astronauts to breathe, and most importantly, the fuel they will need to fly back home. By sending robots first, we're able to hold off sending humans until we know that everything is set up for astronauts to be able to live and work safely.
Okay, wow. So thanks both of you. Those are some very interesting environments you covered. So now we talked through some of the challenges that you've sort of thought about already and experienced. Let's have a look quickly through at the things that the audience might have come up with as potential ideas. So see if this will work for me. I might not update. Helena, do you have access to the main updated one?
Yes, but you have to let me share the screen.
Ah. How do I let you share the screen? Do I just stop sharing? Cool. There we go.
Thank you.
Perfect.
Update.
Okay, well, we can cover a few ideas just off the top of our head while we're waiting for that one to update. I saw there that there was a quick question on a quick suggestion of one of the difficult places robots might have to go to being underwater. Craig, would you be able to comment on potentially some difficulties going on there? So pressures or lack of light and how they might be tackled. Or anything else you can think of?
Yes. So you mentioned earlier about the pressures what are on the seafloor and why we might want to go there, and these will certainly make designing a robot and operating this robot much more difficult than using one on land. A difficulty I can think of off the top of my head is there's no light down there, so especially at the deepest levels. So different types of camera technologies might need to be used, such as LiDAR or sonar.
Okay, cool. Another one I see here is, let's pick. What should we pick? Extreme temperatures. Extreme temperatures. Helena, what do you reckon for extreme temperatures?
Yeah, it's definitely an issue. Electronics need to be kept at the right temperature in order to work. If it's really cold, you need to make sure that you provide a heat source to keep it warm. But if it's really hot, you need to provide mechanics for the heat to dissipate out away from the electronics. This becomes a problem, particularly with space applications, where you have both extremes. On the moon, when you're in shadow, you can get to sort of minus 150 degrees Celsius. But then when you're in direct sunlight, it can go up to 150 degrees. So you've got that really wide range of temperatures, and you need to be able to design for both of them.
Okay. So another one I see right in the center there, big and obvious, is radiation. Craig, do you want to comment on radiation? You work in radioactive environments all the time already, don't you?
Yeah, so this one's right at home for us. And yeah, you're exactly right. Radiation levels certainly make designing these robots difficult. And while a robot can be exposed to radiation, which is why we use them in our fusion reactor, after long periods of exposure, the sensitive electronics can become damaged. And high radiation levels can lead to electrical currents in the semiconductors. And so a semiconductor are the building blocks of digital electronics. And this can cause those semiconductors to randomly open. And then in cameras, radiation produces spots in the image caused by high energy particles hitting the sensor. And ionizing radiation can also break down the materials within the electrical equipment. So to deal with this, engineers develop radiation hardened, or what we call rad-hard components that are more robust and have been tested in these environments. So diamond electronics is like a new and interesting field that could help progress rad-hard components. The problem with current rad-hard technology is that they are often less advanced than the non-rad-hard equivalents. So for example, in cameras, there's a trade-off between robustness and fidelity. A possible workaround is to move sensitive equipment away from the high radiation areas and put all the motor drivers, sensitive electronics and computers in a cubicle, which is connected by wires to the robot, which will be in the radioactive area.
Okay, cool. So we've got a lot of different comments here, and there is another one which I'd be quite nice to cover on sort of what happens if you lose connection or you lose power or there's something happens to the robot. But I think it'd be good actually to sort of briefly, one of you want to comment on that?
Yes, so a loss of connection is, again, it's a good one. We can't, so for example, we can't send a human to recover a robot. Sorry, we can't send a human in to recover a robot if it's disconnected inside a fusion reactor. So loss of connection is certainly one we need to think about a lot. And ways we deal with this is we have comprehensive recovery plans for these scenarios, and our operations team regularly practice the scenarios using various techniques.
Okay, so I notice we're getting quite heavily into the fusion side of things here. Should we talk a little bit more about what a fusion environment is and why it's challenging?
Yes, so fusion reactors are very much a challenging environment. To explain that, I'll give you a quick intro into what fusion is. If you're interested in a more in-depth look at what happens inside fusion reactors, we'll be pointing you to some other talks UKAEA are doing as part of the IF Festival at the end. I would recommend checking those out. John, could you get the presentation up again, please?
Of course.
So I'll carry on while you do that. So fusion is the reaction that happens on the sun. Mostly hydrogen atoms crash together and fuse to make helium. The sun does this all the time. The sun is also very, very big, and that makes it easier to produce fusion energy. By comparison, you can see that the Earth is tiny. So trying to make fusion work on Earth is challenging. So this is the Joint European Torus, or JET, which is housed here in Oxfordshire at UKAEA. JET is how we're trying to make a sun on Earth, as in fact the most powerful fusion machine to date. But like I said, fusion is challenging. To be able to do it, we have to heat the machine to 10 times the temperature at the center of the sun. That's 150 million degrees. And the reaction also produces neutrons, which is a type of radiation. Now, this is when the machine is turned on, but it will still leave a pretty dangerous environment for when we need to do maintenance, and that means we can't be sending in humans. So we have to do it by remote means instead. To do that, we use Mascot, who you can see here. Now, Mascot technically isn't a robot, but a manipulator, and is operated from our control room, which is about 30 meters away from the reactor. So if you go to the next bit, John, you can see one of our operators who's sat far away from the hazardous environment where he's nice and safe. He's got two arms like the ones on Mascot. And when he moves those arms in the control room, Mascot copies the move exactly. And the operator is able to feel everything as they would if they were in the reactor doing it themselves. On the most sensitive setting, if you were to run Mascot's arm over the edge of a piece of paper, you would be able to feel the drop-off when you were operating it. It's that sensitive. And if Mascot picks up something that is 1 kilogram, the operator can feel the same weight in the control room. Though if we were to pick up something heavier, we can change the setting to make it a more comfortable lift for the operator. Now, not just anyone can walk up and use Mascot. You have to be very skilled to be allowed to use it in the reactor. One of the reasons for this is that it's quite difficult to see what you're doing. When you're doing a task in front of you, it's easy to just move and turn your head so that you can get the angles and perspective you need to place things correctly. But that's not possible when you're driving Mascot. You can see Mascot has cameras on the body here at the top and on the arms as well. And there's some cameras put up in vessel. And you can see the views from these cameras on the computer screens in front of our operator. He needs to use all 6 of the views in front of him and stitch those together in his head to get the 3D view that we're used to seeing when we normally do things. It takes many hours of training to be able to do this, but it is vital to operating Mascot efficiently. It costs around an extra £200,000 a day if anything goes wrong. So we're very careful when we design our operations to make sure that everything will go to plan.
Okay. So, I mean, clearly a lot of thought has been put into designing Mascot, and it seems like a very capable robot. Could we use one in other environments? I mean, could we all get house mascots eventually?
So we've envisioned a robot that can go in our house since the 50s. And our depictions of the future often have robots helping us with both dangerous and mundane tasks. Some of you in the audience might remember the Jetsons. However, while we now have more robotic assistants than ever, we still don't have a general purpose robot that can help with any task given to it. And this is perhaps one of the biggest challenges of robotics. They are very good at doing one specific thing very efficiently and accurately. However, if anything new is put in front of these robots, we will not know how to deal with it. So a robot asked to do the same task in a different environment can also cause problems. But we are making progress with robots that are more multifunctional and robots that can be used across different areas for different tasks. And so I have a special guest with me today, and it has been designed to be better able to deal with this challenge. So hopefully, if everything goes right, I would like to welcome you all to Spot.
Yeah. Ooh. That is really cool. What?
So Spot here has a few special features that make it more suitable for a variety of environments. It has laser vision, or what we call LiDAR, which stands for light detection and ranging, so it can be aware of its surroundings and react to obstacles or changes in the environment. You can now see it looking around to view the world as a cloud of 3D information. So there we go. You can see him moving his head around. And from this, it can detect features such as a blockade on a path that is being set. Or if it was in a more autonomous mode, it could navigate around the obstacles. A key difference between Spot here and other mobile robots is that it's quadrupedal, which means it has 4 legs instead of wheels or a tracked base, which is what you may be used to if you've seen other mobile robots. And while wheels are a great way to move around very efficiently on tarmac or concrete, they are useless when it comes to stairs or uneven terrain. Legs allow it to work on a wider variety of surfaces, such as rubble or in industrial environments, which makes it more useful for a wider variety of tasks. Earlier on, you also saw Spot stand itself up from a fallen over position. This is a very important feature if it's to be used in a place that humans can't go. For example, if a robot falls over inside a fusion reactor, we can't walk in there and pick it back up again. It needs to be able to self-recover. And that feature we showed then was an example of it doing this. So these are all cool features. However, perhaps Spot's most important feature is that it can do this. Take it away, Spot. You can see it doing a little dance for us.
What will they think of next? Okay, that's really cool. So, and thank you very much to Spot as well. So, okay, Spot's all very nice and good, but do you think that Spot, this quadrupedal dancing robot, could really help us in our pursuit of safe fusion energy then?
So possibly, we've tested Spot inside our mock-up of the jet fusion reactor, which we call the IVTF, or in-vessel training facility. And this is where we train our remote handling operators to use Mascot and the booms. So it's a one-to-one mock-up of the jet fusion reactor. And perhaps one day Spot could work alongside Mascot-like systems, collaborating with each other to perform operations. You can see a photo of Spot here inside our IVTF.
Cool. And you mentioned that this is sort of a multifunctional robot. That was the general idea, right? So fusion reactors are very specific. So where else could it be used?
So Spot has also been used in hospitals. If we go to the next slide, you can see here a monitor has been added so that Spot can act as a telepresence in the place of a doctor or nurse, so we can interact with quarantine patients without a risk of exposure to a disease. And I suppose this one is currently quite relevant.
Yeah, definitely. Okay, so thank you, both of you, for talking through some of those examples. So we've seen now how, we've sort of shown already how you can use this tool, this robotics as a tool, if you have skilled enough operators and skilled enough designers, to enhance what humanity is capable of. And we can look back at some of the environments we discussed earlier and we looked at earlier, and we can see how people have already come up with ingenious solutions to some of these hazardous places. Whether that's the slothbot in the jungle or robotics in the deep sea, ideas for moon bases or Spot in hospitals, fission plants or fusion experiments, whichever. So we've learned a lot about what's already been done. So why don't we have a think about what some future applications might be? So let's see if the Mentimeter slide works. Cool. If you can think of some futuristic uses for robotics, head on over to Mentimeter, keep that tab open you had before, and share them with us. And hopefully we'll see these things coming in slowly over time. You can see a few answers already ended up there. But if not, we may just reload the slide once we had a few ideas come in. I'll give you a few moments to put in some answers as we have a look at that. Whoop. Sneak peek at what's coming up next. Okay, I can see more ideas, more ideas coming in. So this is good. Okay, so let's have a quick look at some of these ideas. A lot of people seem to want robots to come in and help with housework and homework and all sorts of things. And I'm sure we'd all love the idea of a robot that could help with homework. To a certain extent, we've kind of already got that kind of thing with computers and with calculators and that kind of thing. So you're better off than you would have been a few years ago. So Craig, do you want to quickly comment on driving, which I think is an interesting future application?
Yes. So we were currently at Race. We share an office with a company which are developing self-driving cars, and you can think of a robot as or a self-driving car as a robot for driving. So this is certainly a future use of robots, and I can certainly imagine in the future self-driving cars will be very common.
Sure. I see again also regularly around there's sort of cleaning and cooking and things. You mentioned a little bit before that we're unlikely to see these sort of household robots. You mind explaining a little bit why we're unlikely to see them?
Yeah, so this is because robots typically are very good at doing one specific thing. So the robots are often designed to perform one task repeatably and accurately. However, putting a general purpose robot what can help you out with lots of different things is a much bigger challenge.
So a Roomba would be fine and dishwasher's fine, but you're probably not going to get a combination Roomba dishwasher.
Yeah, exactly.
That's fair. Okay, I can see that there's, let's see, A couple of people have mentioned space as well. We've that's been sort of a reoccurring theme. We'll come on to that in a second. Yeah, actually, yeah. Why not? Let's go and Helena. There must be some good spacey examples of futuristic uses for robots.
Yes, there are. So we mentioned the Moon Village earlier. One of the reasons to do that mission is to test out the technology for going further afield, to say Mars. So this is a concept on the left here of Mars habitat that's been built by robots by NASA. So Mars is much further away and much more expensive to get. So in situ resource utilization, or ISRU, becomes much more important. ISRU is what I was talking about before when I mentioned using resources around you, like moon dust from the moon. So in space travel, the amount of stuff you take with you is very important. Just like when you take an aeroplane, you charge more for a bigger suitcase. By building with things you find when you get there, you can reduce the amount of stuff you need to take with you and save a lot of time and money. And another application for robotics in space is in-orbit manufacturing and maintenance. So we can use robots to maintain satellites to keep them working longer or deorbit them when they stop working. And this could help us tackle the ever-growing problem of space junk. And you can see an image of an artist's impression of space junk. But manufacturing in space could also mean we're able to build things we couldn't before. One example is solar panels. A vacuum is needed to create some of the parts of a solar panel. And we can do that on Earth, but the artificial vacuums made here are nowhere near as good as the vacuum in outer space or even on the moon. If we can manufacture solar panels in space, it would be much more efficient than the ones we have today, making more green power.
That is really cool. Okay. So that's a really interesting sort of couple of combination of examples of what we could do in the future in space. So I guess as a follow-on from that, Craig, from your perspective, is there sort of an equivalent holy grail for robotics as far as you're concerned? So what do you think, say, the challenge that had the biggest impact on our future is, if it were to be overcome?
Well, personally, I'd say that is artificial intelligence. So we've got some slides actually ready for that. You may have seen artificial intelligence, or for short, AI, in movies. And here you can see some examples. We have Jarvis, HAL, iRobot, Data from Star Trek. However, unfortunately, in the real world, we are not quite there yet. So while we have made a lot of progress in AI over the last few years, we're still quite far away from a general intelligence that works in a way like the human brain. Here we have an example of a failed image recognition. And this is a bit of an exaggeration, as image recognition is quite good. But the point to be made is that real AI is very different from movie AI. They tend to be trained to do one specific task, but we can't be given any task and then figure out how to complete it themselves. Having said that, in the future, this might change. So AI researchers sometimes talk about what we call the singularity, which is a hypothetical point in time when artificial intelligence can design better and better versions of themselves, entering a runaway reaction of self-improvement, which results in a super intelligence that surpasses human intelligence. This, however, is hypothetical and it may never happen. Whatever happens with artificial intelligence, though, smarter robots are needed. Some of the operational tasks that we want robots to do are too complex and too unpredictable, such as the dangerous environments we mentioned earlier in this presentation. And if we want to keep humans away from these dangerous places, the robots need to have some level of automation so they can react to changes in the environment as they happen.
Oh, okay. And so you think we're going to be working towards this idea of a silicon brain as time goes by then?
Maybe one day in the future. Yep.
Yeah, interesting. Okay. I know we've talked a little bit about fusion already, but I'm curious, where do these advances in robotics, where does that fit into the future of fusion?
So for fusion to be economically viable, the whole power plant needs to work together, and remote maintenance is a big part of that. A power plant we can't maintain isn't going to last very long or be successful at all. With the robots we've seen today, we can start progressing towards that fusion future, giving clean, unlimited energy for all. JET is currently the biggest and the best, but we are working towards even bigger reactors that will hopefully put power on the grid. These bigger reactors are even more in need of remote handling, as they're not only bigger, but hotter and more radioactive. As I said earlier, it's £200,000 lost a day when JET isn't running, and it will be much more for future machines and power plants. So remote handling is a key technology for enabling fusion.
Okay. Wow. So thank you both. So those are all really interesting concepts, really interesting ideas. We're running towards the end of our time discussing these things, but I hope that people watching have at least learned something about how we use engineering as a tool to tackle these challenges, and how doing this can have and has a huge impact on the future. I think one other lesson that I think it's really key to realize is that robotics is a hugely multidisciplinary field. There's very few other engineering challenges that require expertise from so many different places. You could be a scientist or a programmer or a mechanical engineer or an electrician or a human-robot interaction expert. You could write the laws for it, or you could be part of some sort of campaigning group that pushes for safer environments for workers. 20 years ago, people wouldn't have even heard of the idea of a cybernetics engineer, which half of us here are. So perhaps you could be in some new field that we don't even know about yet. The landscape of robotics changes and evolves so quickly. You can, however, through STEM and STEM-adjacent fields, help towards the future of robotics and humanity together, whether that's through delivering a fusion future like Craig and Helena are working towards, or by tackling any of the myriad challenges a changing world brings. Hopefully, with the knowledge you learned today, you'll be inspired to go forth and save the world with robotics. So, before we move on to taking any questions that you might have, we'd just like to take a moment to highlight some of the sort of upcoming IF events as well that UKAEA is involved with. So you can already go back and look at the previous one on a fusion future. On the 17th of October, we've got the Explorer Zone. Well, you'll have some sort of fun virtual displays for families. 18th of October, super materials for extreme conditions. Sort of imagine that as a counterpart to this one. But looking for more on the sort of materials that we're using. And on 28th of October, we've got Engineering Stars. So, if you want to also find out more about UKAEA, then you can check us out on our socials on Twitter, Facebook, Instagram, YouTube, and LinkedIn. At the UKAEA official on all of those. Or check us out on our website. So, with that, we'll be taking any questions that you might have through the Zoom Q&A facility. So that's a slightly separate thing. So don't just chuck your questions in the chat because you won't read them. Okay, but thank you very much.
Thanks so much, John and Co. That was really an interesting tour of some of the things that robots can do now and potentially in the future. So we've got a couple of questions that have come up in the chat box. One of them is around this notion possibly towards singularity and other kind of artificial intelligences. Do you have a view of when that might become close to reality? At the moment, it's very much sci-fi, right?
Craig, take this one.
So I'm not an artificial intelligence expert, so I can't give you the best answer. But I think really nobody knows. So the recent developments which are making artificial intelligence, such as deep neural networks and image recognition, are getting much better. However, to AI, like full AI, I don't know how long that will be.
It's a little bit like crystal gazing, I think, isn't it? This artificial intelligence question. There's a huge amount of energy and resource directed at it, but we don't really know when it's going to be cracked. Yeah.
It's one of those things that any scale that you see on the approach to singularity is logarithmic. So you never know quite when you're going to cross zero until it's already you're sort of perpetually getting towards this crossover point, closer and closer and closer and closer. But it's interesting.
That's right. So there's been a question around kind of robotic collaboration. And you mentioned that you have a driverless car company that shares the same building. Where else are you kind of collaborating and seeking inspiration from others that are developing different sorts of robotics in different sorts of environments?
So unless, do either of you want to take this? I'm happy to answer this one. Cool. Okay, so one obvious major collaboration we have is with ITER, which is, so we're based at Culham, and most of the research we do is based on the JET fusion experiment. ITER is kind of the next big step in fusion. It's being built in the south of France. It's a hugely international collaboration. There's countries representing sort of over half of the world's population involved in its manufacture. And it's this sort of big project, this big sort of flagship project in fusion. But we also work in general with all sorts of other different groups within the UK. We're involved with university collaborations through RAIN, or Robotics in AI and Nuclear, where it's sort of a mixture of UK universities and UK industry partners. There's a whole host of different ways we collaborate.
Great. Well, there are a few more questions, and we're going to attend to them in a minute. But we said this event was going to end at 7:15, and it's just gone past that now. So I'm going to thank everyone for coming along. We're going to come back to the rest of the questions. If you want to stand to hang by for 5 or 6 minutes or so, we'll cover them all. But I want to thank everyone for coming. I want to again remind you that there are loads more events coming up for the festival, and please do give us feedback. And if you want to make a donation, that would be great too, if you go to the festival donate page. So thanks for coming. We're going to carry on with the questions now, running over time. So if you want to go, please do. But if you want to stay, there are some more questions. And if you have another question, please drop it in the chat box, the Q&A box. So there is a question around putting a colony of people on Mars and the fact that these people might never return, which might not be kind of your area of expertise. But in terms of kind of interplanetary kind of space missions, are there other ideas to kind of develop new technologies for potential kind of off-planet kind of either manufacturing or cohabitation or other kind of things that are happening off-planet that you're thinking about maybe?
Yeah, so there are some plans to go to Mars and not bring people back, but there are certain organizations like NASA and ESA that aren't too keen on those ideas, ethically speaking. But there are other things. So it's looking at mining asteroids is one thing, and mining other places without necessarily the need for humans. You send robots, you can mine and get these resources that are useful, and then use them to manufacture in space. Like I was saying, for example, with solar panels, you can get silicon from the dust available on the moon. And you've got that vacuum that's useful for manufacturing them. So you could do it all on the moon, which is pretty cool.
So one of the questions we've also had, so I'd never heard of a mechatronics engineer when I was at school. It probably didn't exist. And so there are loads of, so the robotics and different sorts of kind of computer technologies are opening up brand new kind of areas of human endeavor and creativity. So there's one question about what is your favorite robot and why? And then there's another question, so what do cybernetics engineers actually do? So I think that's a question for everybody. What's your favorite robot and why?
Does it have to be a real robot?
It has to be a real robot. It can't be the cleaner from the Jetsons with a sassy attitude.
I think Smart Money's on spot for quite a lot of them. It's actually a really hugely cool piece of kit that they've got there. And it's one of the most sort of comprehensively good at traveling over different terrains of any robot that I've really seen. So we've actually got some test lanes based in the Oxford site where we can test all sorts of different rovers, so ground rovers and all sorts of things, over a series of deliberately incredibly challenging types of terrain, so stepped terrain or gravel and sand and that kind of thing. I think Spot is the only robot I've seen that has tackled all of those without major fault. So it really is quite impressive in terms of its ability to move around and see things.
I think I would say Canadarm. So I noticed on on the question we asked about future robots, somebody put extra vehicular activity, or EVAs, which is when astronauts go out of the safe habitat in a suit. So this is on the ISS, that's when they go outside into actual outer space. And Canadarm is this robot arm that is on the outside of the International Space Station, and at the minute assists EVAs, but maybe future robotics could completely get rid of the need for humans to go into that extra dangerous environment.
So I'd say mine is either Spot behind me, or potentially we have another robot at race called Tom. And Tom is a very old, big robot. As it was built in either originally built in either the 70s or 80s. I can't remember.
70s, I think.
70s. But we've recently repurposed it, and it's definitely got sort of like a personality to it, and yeah, I'm very fond of the Tom.
Okay, cool. So there's another question, a couple of questions actually that are around the human integration with robotic systems. And one example someone has asked about is driverless cars and humans and that kind of area of work. And you mentioned obviously the robot arm that is used inside the fusion reactor, which has its own kind of challenges around kind of operating it, takes a particular level of skill. What are the key challenges, would you say, that are present when humans and robots have to kind of work together cooperatively?
So I'll let everyone else have a shot at this question as well, but the way that humans are sort of wired up to interact with the world isn't necessarily the same way that we design a robot to do it. So finding a way of making your robot interact with the world and you interact with the robot in a way that's intuitive is a real challenge. So you saw with Mascot, we've got these sort of dangly arms and things, so it's as much a one-to-one representation as possible. But even then, that does require training to get into using. If you imagine that instead of having pincer for grippers, you had active surfaces, for instance, that can fully fit around an object and pick it up and hold it in place in ways that your hand, you can't visualize using because you don't have sort of, I don't know, rollers on your fingerprints, if that makes sense. Mm-hmm. Finding ways of making these interactions work in an intuitive way is really key. And there's research groups that just look at how you actually interact with robots rather than necessarily even use them, just how you interact with robots in an efficient way.
I think we've all had experience of that when our mobile phones have an update and the gestures function changes and you need to now swipe or pinch or do something else, and so how do it's that difficulty, isn't it, of how humans' natural kind of behavior can correlate accurately with what a computer or a robotic system can do. Okay, and so then we've got a question about in the future. So if we got our crystal balls out for a second, in the next kind of 30 or 40 years, when we're all, when you're getting to retirement age, where do you think robots will be in terms of the kind of workforce market?
Ooh.
And what do you think they'll be capable of?
So I think driverless cars will be much more common in that time scale. Beyond that, as you said, it's hard to tell really.
Yeah, just think of the difference, the change we've seen in the last 30 years. So since the 90s, it looks completely different now. And probably nobody would have been able to guess what it looks like. So it's quite difficult. It's a fast changing field.
If anyone does know and gets it right, then they'll be very, very rich. So,
I mean, you mentioned, Craig, the kind of difference between that robot, your two favourites, kind of Spot, and that kind of older robot with its own sort of idiosyncratic way of working. And so the way that kind of even the robotics field, as you're saying, Helena, has changed in the past kind of 10, 20, maybe even 30 years. Who knows where things are going to be in 30 years from time. And I think it's probably up to some of the members of our audience, if there are some young people kind of watching, it's going to be them who get to choose the direction of travel of robotic systems and kind of computer development. So hopefully this event tonight has inspired people to think how they might be involved in robotics, and how we can all benefit from having more machines in our lives that can take the brunt and the grunt work out, and we can be more creative as humans. Thank you again for the talk. Thanks for our audience for staying behind a little bit later than we had planned, but I think the questions were good enough to kind of warrant that. And we'll look forward to seeing you in the future. Please give us feedback, and if you'd like to make a donation, do that too. Bye-bye.